I didn't get
At least it says it is on my computer.
Okay, let's go for it then. So thanks everyone for joining. I'm Finley. I'm part of Safe Landing. I'm an aerospace engineer. Our group is for any aviation worker anywhere in the world. We've got pilots, cabin crew, airport workers, air traffic controllers, engineers, factory workers. If you're connected to aviation, if you're part of the sector, maybe you used to be an aviation worker and you've left, we're keen to hear from you. We're keen for you to be involved and contribute to our group. Um, Basically, we're trying to reduce the environmental impact of the sector as rapidly as possible in any way that we can really think of and support and empower each other to do that. This is our website and this is our email. So please reach out to us on social media or via email if you want to discuss anything and get involved in any way whatsoever. Um, we've got a couple of positions, principles as a group. We want our industry to be honest about the total environmental impact of flying. We want it to be realistic about the limits of technology to solve the problem. We want it to be transparent about future regulations that are required to reduce emissions. And we want to have a plan that accounts for all of that and supports workers as we transition and transform the industry towards a low environmental impact future. Now, really excited about the presentation today. We've got Georgi Atanasov here. He's from the German Aerospace Centre, or DLR, based in Hamburg in Germany. Now, this is a topic, flying slower, that I've been quite passionate about for a long time. We understand we've got a carbon budget, and also in terms of how much fossil fuel we can keep on burning. And we've also got limited resources when it comes to non-fossil fuel. So it's really important we fly as efficiently as possible so we can maximize how much we can fly in that budget. And also flying slower is a potential way of doing that, as he'll take you through. But also the interesting thing from a safe landing perspective is maybe this will also allow us to increase jobs, even potentially within the constraints of flying less overall. We might be able to have a rebound in employment because we're decelerating how we travel. So really interested to hear some more of the technical input behind that. So Georgi, thanks for being here, and I'll hand over to you and let you take people through it.
Okay, thanks, Finley. So hello, everyone. As Finley mentioned, my name is Georgi Atanasov. I'm working for the German Aerospace Centre, in short DLR, at the Institute for System Architectures in Aeronautics. I'm a senior in the overall aircraft design team. So our specialty or our capability is to create aircraft models for technology integration, for example, new propulsion technologies or system technologies or energy carriers, and provide them for assessment studies, for example, for global fleet assessment, climate impact, and so on. So we basically design, our main job is to design aircraft and assess them and improve the understanding of how different technologies can be integrated into aircraft design. So today the topic is how slow should we go, and on this topic there is not very much literature or knowledge gathered, and this was something that we needed to improve in the past years. And there was this huge project, a DLR internal project, Exact. So not everybody knows it, but there we did gain a lot of understanding on the topic, and the knowledge we got is quite interesting. So I'll try to share it with you. And yeah, so for this presentation today, we have first I start with the basics. Why is flight speed important? Then we have, or how is it important? Then I'll be introducing the DLR project Exact, followed by the description of a turboprop design, within this exact project, and a global fleet assessment of the study, and followed by a summary. So about the basics. If we look into simple forward flight, level flight of an aircraft, then we have lift equals weight and we have thrust equals drag. So it's a really simple case, and the aircraft needs to move from A to B. So first question is, what is the energy needed to transfer from A to B? The energy is power times time, so proportional energy times time, but it can be also rewritten as thrust times distance. So this is the same two equations. Work equals force times distance. So what the conclusion is, because the drag basically can be described as the mass of, or the weight of the aircraft divided by the L over D. So L over D is the aerodynamic efficiency of the aircraft. Basically, the energy to move an aircraft from A to B is the distance multiplied by the the mass of the weight of the aircraft divided by the aerodynamic efficiency are proportional to this energy. So if the distance is fixed, the only two parameters we have left are the mass of the aircraft and the aerodynamic efficiency. So if two aircraft have the same mass and the same aerodynamic efficiency, then you need the same energy to move both aircraft from A to B. What comes additionally is the propulsion chain. So this energy comes from the propeller or the fan of the aircraft. And basically the shaft energy is then the propulsion energy divided by the propulsor efficiency. And then we can go further down the chain after the gas turbine. So the gas turbine is the usual provider of this power. The fuel energy is the shaft energy divided by the gas turbine efficiency. So we have the fuel energy is basically then proportional to the mass of the aircraft, the aerodynamic efficiency, and the propulsion efficiency. So the gas turbine efficiency and the propulsor efficiency, basically. So this is the first order effect for to move an aircraft from A to B. And flight speed is not directly here in these parameters, but it can affect those. So it can affect the design such that these parameters change a bit. So usually we have, when we see an airliner, it has a look that is similar to this one. So transonic airliner with Mach speeds of over 0.76 typically. And so all of them which are in these transonic speeds, they have swept back wing and usually turbofan engines. Turboprop propellers are not the typical design choice, or are not a suitable one, because propellers do not operate really well or really efficient at speeds close to the sound barrier. Counter-rotating propellers or open fans can be more efficient, significantly more efficient than turbofans, but they come at the cost of high engine noise levels. So they also usually don't make it to product, to final products. So what happens if we switch to subsonic speed? So first of all, turboprop engines become a suitable design choice. Propellers designed for subsonic speeds can be really efficient. And they're also much larger than fans. So they can move much more air, basically, and require much less power for takeoff. This is one effect that's not widely recognized or paid attention to, because it's not just about efficiency in cruise, but it's also about power in takeoff. And it changes things a lot. So you require smaller engines in the end. So non-swept wings is another feature that's possible when we shift to subsonic speeds, and they allow higher lift coefficients at low speeds, so smaller wings are possible for takeoff and landing. Better compatibility with laminar flow technologies due to the lack of sweep. So laminar flow control or natural laminar wing are much easier to and much more efficient, much more efficiently implemented for such wings. And also they can be built thicker, so structurally thicker, so lighter than a typical swept-back wing for transonic operation. So overall, as a summary, shifting from transonic cruise speeds to subsonic cruise speeds can enable more efficient propulsion, lighter structures, and improved aerodynamics. And overall improved flight efficiency usually enhances any additional sustainability solutions. So it's always, so efficiency is always the base for sustainability. So a couple of words about the DLR project exact that I mentioned. It started in 2020, 4 years ago, and finished last year. Back then, there were a lot of open questions about sustainability and research topics starting to arise at an increasing rate. So there was a lot of need for improving the understanding of how aviation sustainability can be improved and what strategies should be taken politically. And because of this, we had to try to answer a lot of these questions, and this gave way for a large project, which basically tries to answer those. And answering such questions cannot be done in a small project, or not satisfactorily, at least. So you need a lot of disciplines to assess. One has to try to capture the whole picture, from energy production to air traffic demand and air networks to aircraft design, which basically builds the bridge to the climate impact. So from energy production and propulsion technologies to air traffic to aircraft design and then to climate impact. So everything needed to be looped in this project, and it got a lot of funding volume, basically 20 million euros for these 4 years, with a consortium of 20 DLR institutes. So it bundled quite a significant portion of the DLR capabilities, and it was a really interesting project to be part of. So on the aircraft model side, as mentioned, the aircraft models needed to build a bridge between the global assessment and the technological assessment. And we had to expand a lot of knowledge and know-how and create new tools to enable consistent aircraft design for multiple for different aircraft propulsion technologies and energy carriers, and also for different aircraft classes. So it was a difficult challenge because usually you have a project where you have one aircraft and it needs to be calculated and assessed versus a conventional aircraft. This is a typical project. In this case, we had to answer a lot of questions, so we needed a lot of different aircraft calculated, and they needed to be calculated in a consistent manner, comparable to each other. So basically, they had to be compared consistently with each other. And this was a significant challenge, but it was also, we set some boundaries. So basically, the focus was only on short, medium range class and the regional class. We had the reference aircraft there. So this is the starting point, like the typical airliners for these two classes. The baseline aircraft, they are assumed to be kerosene fueled, and the advancements, so they're designed for the year entry to service of 2040. And they only evolutionary advancements of propulsion and airframe are assumed for them. Then there are the direct burn concepts for with hydrogen and hybrid electric propulsion concepts, clusters basically. But the focus on the presentation is on these conventional aircraft. So the study speed versus sustainability, which led to quite improved understanding of the effects and the enablers of switching to subsonic flight at the larger aircraft classes. And this is what I'm going to be focusing on this presentation in the further slides. So we have the boundary conditions for this study. The starting point is a A321 neo-like aircraft. So it's an interpretation of the DLR on this aircraft. It's a model that we created to basically try to imitate the aircraft. And it has these typical TILAs, top-level aircraft requirements. So the typical design range of the aircraft with the maximum payload and takeoff field length requirement for the aircraft. And these are used as a base for our designs with some changes. So the TILAs are changed now to a bit shorter. So the A321 usually is calculated with a design range of, or the base version at least, with 2,500 nautical miles. The range is shifted to lower range capabilities because we're trying to assess the shorter spectrum of the market in exact, and the focus was on sustainability. So reduced range helps a bit with this, and this is the range assumed for all the aircraft in this class in exact. Then we have slightly reduced takeoff field length because of the shorter range. So denser network needs to be serviced. Also a bit larger passenger capacity, also to improve sustainability. And there are some technology changes like improved gas turbines, better materials for the airframe, and CFRP wing with foldable wingtips and a bleedless systems architecture. And using these requirements, so exact, derived for exact, then these two aircraft are created and compared to each other. We have a typical turbofan with this technology improvements, and then we have a turboprop, and this turbofan has basically the same characteristic as this A321 and these new requirements, of course. And a turboprop, but for the turboprop we have the Mach number open, so there is no comparable product to start from, so we needed to start from scratch, and cruise Mach number needed to be optimized. So about the turbofan, this is the ladder chart showing the design fuel, the design mission fuel of this aircraft as compared to a state-of-the-art airliner. So we have some improvement due to reduced mass, improved aerodynamic efficiency, also improved propulsion efficiency, or better gas turbines, and higher bypass ratio, which is a result of the better gas turbines. And then we have also, so there is this intermediate step with a winglet model or improved future airliner with winglets. But then we also included the foldable wingtip solution, so basically even higher span to improve the aerodynamics even further. And overall, with just conventional technologies, they allow improving the fuel efficiency by about 20%. Truss-braced wing and laminar flow technologies are not included in the study, so these were off. This is not in the spectrum of the study, but they could allow even better performance in the end. And this is the turbofan that the turboprop then will be compared to. So this 20% better turbofan than the conventional reference one. So this is the turboprop design. We have with the basic intention to trade speed versus efficiency. The design, the global fleet, the design KPI is the global fleet operating cost of the aircraft. So it's not just on block fuel or the optimization, but on the global fleet operation costs. Only unswept wing design was considered to avoid even further complications and complexity in the modeling. So this was one boundary condition that we set for the study. So this required also Mach numbers below Mach 0.7 or Mach 0.7 and below. The low wing configuration could be kept. So it's the same wing below the fuselage as in the A320, for example. It's possible with slightly gulled wing, despite the large propellers. Propeller blade off shielding is also included in the fuselage structural model, so the passengers are protected if basically a blade comes off during operation. T-tail was implemented to avoid the empennage being in the wake of the propellers in the slipstream. And this configuration was fixed, and the cruise Mach number was optimized in terms of fleet operating costs, or at least traded, not really optimized, as I will show. A couple of different configurational features. So we have slightly shorter fuselage because of the different empennage. The APU can be shifted a bit back below the vertical tail, so we get a little bit shorter fuselage. Then, due to the gull, as mentioned, we can have a propeller which is aligned with the leading edge. So the middle axis of the propeller is aligned with the leading edge of the wing. And so when the center axis is shifted upwards, there is enough space below the wing, because if you have just a turbofan, you cannot align it with the wing. It has to be below the wing. So it's a comparable integration space-wise, or at least vertically. And the landing gear could be designed a little bit smaller due to the gull. So without a gull, I would have a similar landing gear length, but then the landing gear would be inside the slipstream of the propeller, because it still needs to be retracted. So if it's too long, it needs to move outward, and if it's inside the slipstream, then it will be really noisy in takeoff. So these kind of aspects were considered in the design. Also, the structural design of the wing. So this is a typical Yehudi kink that we have in a A320 configuration. And the landing gear is integrated between auxiliary spar behind which joins the rear spar of the wing. And the landing gear is integrated between these two and attached to these two. And the turbofan design has a similar arrangement, and because of the higher span of 42 meters due to the foldable wingtips, the landing gear needs to shift a bit backwards, but it's still within an acceptable range, so it needs to be tilted a bit for the integration, and still retracted here in the middle between these two spars. But it's possible. For a turboprop with an unswept wing, it's easier. So unswept wing can not only be built a bit thicker, but it's also easier to integrate the landing gear inside between the two spars. But it still needs a kink. So it's not a Yehudi kink, but it's a similar concept due to the landing gear integration. Okay, aerodynamic performance. Usually, so this is the aerodynamic performance of the baseline. It has an LOD of about 20, which is good, and it's mostly a result of the high span. due to the foldable wingtips. The turboprop can achieve even more, and this is not mainly because it has less drag, less friction drag. It does have a bit less because of the engine surface area primarily, and a bit shorter fuselage. So this is the total wetted area, but it's still it's a bit less than the turbofan. It's significantly less, but it's still not that. Yeah, I guess it's in the same order of magnitude. So 10% drag improvement. So 10% less wetted area, much smaller wing. As mentioned, it can produce more lift due to the unswept architecture, and smaller engines, basically. And then we have the additional effect of, because it's unswept, and there is the 3D effects at higher lift coefficients are less challenging to work with for unswept wings. So increasing the lift coefficient is a bit less challenging for unswept wings, and it can make use of the increased aspect ratio even better than a typical. So in this case, we have a larger wing, significantly larger, and so a significantly smaller aspect ratio. And also this one also shifts the lift coefficients more outward. So basically utilizes the lift a bit better. But overall, it's not like it's not 20-30% better in terms of aerodynamics, despite all the advantages. It's like between 7 and 10%, depending on the Mach number, design Mach number of the aircraft. So the slower versions of Mach number of 0.66 get a bit better improvement, and it flattens out the improvement basically for the smaller Mach numbers. So the mass of the aircraft, if you compare again different Mach number designs, the slower an aircraft goes, the better, or the less heavy it gets, which is mainly because of the gas turbine mass. So this is the fuel, payload, and systems are assumed the same for these aircraft. Then we have the propulsion, which gets lighter the slower the aircraft goes, and the airframe structural elements. So the wing is a bit lighter, and there are some snowball effects overall. So we get the main effect, or the main variable, is basically the propulsion mass and the efficiency. So less fuel and less propulsion mass. And yeah, the gas turbines are smaller because the aircraft is getting slower. So flying slower means less power for cruise. And the aircraft also requires much less power for takeoff, as I already mentioned, and I'll show in the next slide why. But these advantages are flattening out also. So below Mach 0.66, you don't get significantly more advantage in terms of mass. So first of all, on the turbofan versus turboprop efficiency increase, just an explanation example. The main difference between the two is the large propeller diameter, and why it can be built large is mainly because the turbofan requires a high fan pressure ratio. So high fan pressure ratio means the pressure jumps behind the fan, and one thing that it does to compensate is because the duct is there, and the duct creates pressure losses of around 1.5%. So the pressure drops till the end of the fan by 1.5%. So you need a high fan pressure ratio just to overcompensate. So basically you need to overcompensate this pressure drop, and then it doesn't need to be significant. So it needs to be insignificant compared to the fan pressure ratio, because if you have a fan pressure of 5%, for example, 1.05, and a drop of 1.5%, then you squander a lot of energy, basically. So it needs to be negligible compared to the fan pressure ratio. That's why 1.35 is actually quite low, and it's enabled by a low pressure drop in the nacelle. But the propeller doesn't have this problem, so it has a 2% fan pressure ratio increase. Fan pressure in 1.02, and this is because of the large area. And what it means is that the turbofan gets much less air through it than a turboprop. So it needs to accelerate the air much more to get significant thrust than a propeller needs to. So this leads to propulsive efficiency drop. So we have a propulsive efficiency of the propeller just 2% efficiency drop due to the slow acceleration, and a turbofan, because it accelerates the air quite a lot, the efficiency drop, propulsive efficiency drop automatically before the other losses. It's already 14%. So overall efficiency of the turbofan is about 76%, and the turboprop in this case is about 86%. And this is mainly because there is no duct. So this is the enabler. Okay, I won't go too much into it. There's a plot that, of the propeller efficiency with variation of design Mach number. It drops significantly the larger the Mach number, and this is the efficiency in comparison. So the efficiency of the turbofan. So you can see at some point you don't want a turboprop anymore, but in this area it's quite good. This is the low speed case. So this is quite interesting, and I need to show it. It's, if you look into static thrust, so this is the Mach number, and required gas turbine power output to generate 120 kilonewtons of thrust. Just an example, it's not a calculation of the aircraft. Just an example, if I'm at static conditions, I need this amount of power with a turbofan and with a turboprop to generate the same thrust. And it's basically this helicopter effect. A large rotor needs to accelerate the air quite, not by a huge amount, just by a little to get the thrust. And it requires much less power. So the more you need to accelerate the air, the more power you need. And it transfers even to end of field conditions, and it even grows in proportion in this case. So a turbofan needs to be much larger, basically, to generate the thrust needed for takeoff than a turboprop. And the implication is basically a turboprop aircraft needs much smaller gas turbines. And to avoid oversizing the gas turbines for climb, so if you set too challenging conditions for climb, for example, set the aircraft to climb to really high altitudes, then this starts to be the driving point for your gas turbine design. So to avoid this, typically turboprop aircraft get lower design altitudes. So it matches the takeoff power requirement, basically. So this is why the better match for turboprops is lower altitude flight. So smaller gas turbines is not always good, not good in all aspects. They are lighter and cheaper, but also they're less efficient. So this is a generic gas turbine efficiency curve used in Exact. We have the power class here, which is basically the power of the gas turbine at sea level conditions at maximum temperature. So just for comparison of the classes, so a comparable point. And the efficiency of the gas turbine in cruise. The turboprop gas turbines are much smaller, but also less efficient. So this dampens the advantages a bit. So what happens is we have the following combination of effects that I explained before. So mass, aerodynamics, then the efficiency penalty of the gas turbine, large gearbox, two-stage gearbox needed for the large propellers, also a penalty. And then we have block fuel improvement due to propulsive efficiency of the propellers versus ducted fans, and improvement of the allowances and descent, so of design operation. Overall, for 1,500 nautical miles, the turboprop is like 20% better in terms of block fuel. This is a Mach 0.66 version. One additional aspect, very important one, as it turns out, the allowances or landing takeoff cycle. Basically, you have takeoff fuel, taxi fuel, approach and landing fuel. They're much less with smaller gas turbines. So when you need a lot less power for takeoff, you also use a lot less fuel for takeoff. And the same goes for taxi and approach and landing. If your gas turbines are much smaller, they burn much less fuel during idle conditions. So overall, a lot of fuel can be saved in these phases. You see the fuel for the turbofan is about 500 kilograms just at the airport, and it gets to about 350 kilograms for a turboprops, which is quite significant for lower range. So if you look at the distances flown, and this is the block fuel, this is the block fuel lines for the turboprop and the block fuel line for the turbofan. You see 2 tons of fuel for 300 nautical miles mission. So basically Hamburg, Munich, no, a bit less, but about this range. A quarter is for landing takeoff cycle. So quite a lot is just burnt at the airport. And because of this, the relative savings, so these are the lines for relative savings. You see the relative saving at 1,500 nautical miles is about 20% of a turboprop with Mach 0.66, but it improves to about 30% at the shorter missions. So this is quite a significant aspect of turboprop operation. And similar effect can be traced for block time. So mission time is penalty for Mach 0.66 turboprop is about 12% penalty, but the penalty is just between 5 and 10% for the shorter missions, because a lot of the mission is just around the airport, so it doesn't affect cruise speed, doesn't affect it. So the biggest advantage comes actually at lower distances for such a turboprop. So a turboprop operating intracontinentally can be really beneficial without many penalties, actually. So global fleet level assessment. In exact, it was calculated. So basically, it simulated a global operator with 500 machines at many different routes throughout for the whole cycle of the aircraft. So basically, the simulation included its whole course of its life, and it was used to calculate the fleet yearly operating costs and the total fleet climate impact for this simulation. And it included material production, logistics, and also the maintenance checks, overhaul, crew costs, day-night cycle effects, and so on. So everything was included in this global assessment. And it was a collaboration effort, including the over aircraft design disciplines of 12 institutes, so this whole exercise. So it was quite an extensive assessment. About the fleet operating cost per ASK, so per passenger per kilometer, basically, available seat kilometers. We have here 3 different lines with fossil fuel in 2050, with SAF in 2050, and with 2 scenarios. So basically base cost scenario for SAF and high cost scenario for SAF. And if you get this point, you can see that the optimum tends toward these two Mach numbers, as does the fuel efficiency as well. And here's shown a breakdown. I guess it's you can look at it after the presentation for more details. There's not too much to say, but what makes a positive impression is that it's relatively flat, the effect. So you can have this design or this design, and it won't be much different in terms of cost. And it's also better in terms of operating cost than turbofan, at least for the boundary conditions that were considered inexact. But the biggest highlight was the climate impact assessment. So we have reference aircraft, so this is the A320 as the starting point. Turbofan with fossil fuels, advanced turbofan with fossil fuels will be about 20% better in terms of climate impact. And a turboprop will be about 44% better. So it's not just the fuel reduction. So fuel reduction is basically in comparison to the A320, you get about 40% less fuel needs, but also NOx effects due to reduced altitude and the contrail effects add up, and you get a lot of additional improvement. So if we go further and try to solve contrail impact, like with specialized contrail avoidance, this impact can be dropped to really significant levels. Also, if we go into synthetic fuels, then the turboprop with synthetic fuels can allow a reduction of 70%. So a turbofan would halve it a bit, approximately. But turbofan would give a 70% improvement overall. And solving contrails could push it to 90 or more. So this is quite significant. Flying a bit slower, this is Mach 0.66, sorry, enables quite significant boost in sustainability potential. Yeah, I don't know if I need to elaborate on the summary, so I'm over time a bit. Sorry about that, Finley. But the highlight is you can have a lot of improved efficiency due to shift to subsonic flight and shift to turboprop propulsion. And the price you pay is 15% speed reduction. So it's not like you need to go 2 times slower. You're going 15% slower, and you gain much more improvement potential than this penalty. This is the basic highlight. And yes, there are uncertainties. So exact was more top level assessment. So because we had to incorporate a lot of effects and a lot of characteristics and parameters and quite a lot of modeling. So some of those were top level, including costs and climate impact. So only a basic empirical NOx emissions model for the gas turbine, for example, and some uncertainties in the impact of non-CO2 effects. But the whole picture is consistent within itself. So it's a good indication that this should be looked into further. And we're doing that in Exact 2.
Brilliant.
Okay.
Thanks very much. And yeah, do you want to stop recording if possible?